Fantastic.
Yes, so we are happy to introduce our last speaker for today, Anna Stelzer from Urbana-Champaign, speaking about Gröbner crystal structures. Please go ahead.
Yes, thank you very much for the opportunity to speak here today. I'm going to be presenting on some joint work that I've been doing with Abigail Price and Alex Yong. So let's see. Okay, there we go. Today, I'd like to talk about the determinantal varieties as sort of a motivating example. So these are varieties that live in the affine space of m by n complex valued matrices. And the nice thing about this particular affine space is that it comes to us with an implied group action on it. The group that I'm going to call boldface GL is a product of general linear groups GLM and GLN, and it acts on the space of matrices by matrix multiplication. The factor of GLM acts by multiplication on the left, which is to say elementary row operations on our matrices, and the factor of GLN acts by multiplication on the right, which is to say column operations. And the classical determinantal varieties are then just the sets of all m by n matrices of rank at most k for each choice of k. And these varieties show up in algebraic geometry, representation theory, invariant theory, several branches of math. And they are special from the perspective of this group action. They are the only irreducible varieties in the space of matrices that are stable under this boldface GL action. And that's basically just a fancy way of saying that the only invariant of a matrix under arbitrary row and column operations is its rank. Okay. So, given that these varieties are of interest in many fields of math and they are special from the perspective of this group action, it makes sense to try and use the group action as a sort of symmetry to organize our computations. So we can ask what this GL action reveals about a classical determinantal variety. And there are multiple ways to interpret that question, but for today, I want to interpret it as asking about the coordinate ring of polynomial functions on these varieties as a GL representation. So I'll remind you, in case you're not a representation theorist, that the irreducible representations of GLN are called Schur modules. I'm going to denote them by V sub lambda of n today, where lambda is a partition with at most n parts. And about 50 years ago, Dubélé, Rota, and Stein proved a beautiful theorem where they showed that the coordinate ring of each classical determinantal variety as a boldface GL representation has a very nice irreducible decomposition. You can see here we have the decomposition and it is multiplicity free. So every irreducible representation that occurs exactly once. And the irreducible representations of boldface GL are tensor products of Schur modules, one for each factor of GL. And the Schur modules that appear here are paired. They're indexed by the same partition. And the partitions that occur are exactly those that have at most k parts for whatever k is indexing our classical determinantal variety. So this is a very, very nice expression. And the goal of the talk today is going to be to provide sort of a general flexible method for proving decomposition results like this and giving combinatorial rules for the irreducible representation multiplicities inside coordinate rings. Okay, so here's our main question. If we have an embedded variety embedded in some affine space, and it carries some reductive group action, in this talk that's basically just going to be GL or products of GLs, how do we decompose the coordinate ring as a representation? And in combinatorial representation theory, people have developed really powerful techniques for doing this. To give a brief outline, what you'll often do is you will construct a nice vector space basis for whatever representation you're studying. If you're an expert, by nice, I mean that it is homogeneous with respect to the maximal torus inside of G. If you don't know what that means, don't worry about it. This is just like usually not too difficult of a condition to satisfy. And then once we have a nice basis, we're going to try to turn that basis into a crystal graph by viewing the basis vectors as vertices and then drawing in edges according to certain axioms that we think of as representing local moves between the different basis vectors. And if we're able to define this crystal graph structure in a way that satisfies the axioms for these things, then that will give a combinatorial rule that computes the irreducible representation multiplicities we're after. So Hopefully, over the next 5 or 7 minutes, I can give you a little bit more detail on what it looks like to apply this general technique to the situation that we care about, namely these coordinate rings of varieties, like the classical determinantal varieties. Okay, so first step in our procedure, if we have some embedded variety in some affine space, how do we get a vector space basis for its coordinate ring? Well, there's one case where this is easy to answer. If our variety is just affine space, then the coordinate ring of affine space is a polynomial ring in however many variables. And if we've chosen coordinates for our affine space and are doing everything explicitly, then that polynomial ring comes with an explicit vector space basis, namely the basis of monomials, right? Every polynomial is a linear combination of monomials. And in general, if we have some variety that's been embedded into our affine space, we can use the method of Gröbner degeneration to algorithmically compute a subset of the monomial basis, which we call the standard monomials for our variety x, that then form a vector space basis for the coordinate ring of x, which we realize explicitly as a quotient of our polynomial. So to give you a very simple example of how that works, let's take the variety defined by the equation y equals x in the xy plane. The coordinate ring of this variety is a polynomial ring in x and y, quotiented by the relation that x is equal to y. Um, so if we want to define a vector space basis for this quotient of monomials, we know that we can't have both x and y because they're obviously linearly dependent. They are equal to each other in the quotient. But how do we decide which one of those we want to keep as our basis vector and which one we want to throw away as dependent? The idea of Gröbner degeneration is that we fix some term order. In this case, I've said that y is like a bigger variable than x. And then if we've chosen appropriate equations for our variety, we can just kind of truncate them. And instead of considering the variety defined by our original equations, we can just take the variety defined by the lead terms of those equations being set to 0. So that geometrically degenerates your variety from whatever wild shape it was into a union of coordinate subspaces. In this case, we've taken our diagonal line and we've degenerated it onto the x-axis. And now, if we think about the quotient by our degenerated equations, there's no ambiguity about what our monomial basis should be. Any monomial that contains y in it is going to be equal to 0 in the quotient, and so our linearly independent basis should be all the powers of x. And the magic of Gröbner degeneration is that this basis of monomials we get from the degenerated variety will actually be a vector space basis for the original quotient. Okay. So this is great, but if we're interested in doing representation theory and figuring out these sort of irreducible representation multiplicities, Gröbner degeneration doesn't initially seem that helpful because if we start out with a variety that has some large group action on it and a lot of symmetry, the degeneration is pretty destructive to that symmetry. It will preserve torus actions, but it won't preserve larger group actions like GL or products of GLs. So this is where the crystal basis or crystal graph methods come in handy. They're going to allow us to recover sort of from the shadows of our degeneration what the original representation decomposition must have been. So to introduce crystal graphs, let's go back to the Schur modules, which so far I've only told you are some irreducible representations indexed by partitions. It turns out that they have basis vectors that are given by combinatorial objects called semi-standard Yong tableau, and we can use these to build our first examples of crystal graphs. So if you don't know what a semi-standard Yong tableau is, take your favorite partition and represent it using its Yong diagram. In this case, my partition is 2, 1, which I represent with the Yong diagram having 2 boxes in its first row and 1 box in its second row. And then a semi-standard Yong tableau of that shape is a filling of the boxes with numbers that are weakly increasing along the rows and strictly increasing along the columns. And if I'm thinking about GLN representations, I'm going to use numbers from 1 to n. So in this case, I'm using numbers from 1 to 3, and there are 8 semi-standard Yong tableau. Okay. So this is the crystal graph on this set of tableau. I haven't defined the crystal operators yet, but you can see that we have some edges that are red labeled E1 and some edges that are blue labeled E2. And if we follow one of these edges, like this one in the upper left here, the effect of following an EI arrow is to change a single I plus 1 in your tableau, in this case this 2, into a 1. So you change an I plus 1 into an I. And so these are like local moves between the basis vectors that are required to satisfy some axioms that I'm not going to tell you today. Okay. And in case you're curious about the technical definitions of these things, from each tableau, there's a way of reading the entries to produce a word. And then we define the crystal operator EI by forming like parenthesis sequences from the word, turning the i's and I plus ones into certain parentheses. And then the rule has to do with taking one of the unmatched parentheses in this sequence and flipping it. The exact details aren't going to be super important for us today, but that's the flavor of it. And the parenthesis matching ensures that if we start with a semi-standard Young tableau and we apply this operator, we will always get another semi-standard Young tableau. Okay. And within these crystal graphs, we actually heard about this a little bit in the last talk. We have vertices that are highest weight, or Yamanouchi, which means that when we form the parenthesis matching sequences, there are no unmatched parentheses that we can flip for any I. And so this is an example where I just drew part of a tableau in, so you could see the part that's used to look at the E3 operator. And there's no unmatched open parentheses here, which means that this particular E3 operator will output nothing. And so a vertex that is highest weight will be a sink in our crystal graphs. And every connected component of a crystal graph has a unique highest weight vertex. And this is good news for combinatorialists because it gives you a way to like identify the whole connected component of the crystal graph just by looking at a single basis vector. So in our Tableau crystal graphs, we can explicitly identify the highest weight vectors. They're the super semi-standard or Yamanouchi tableau that have all ones in the first row, all twos in the second row, all threes in the third row, and so on. And this tells us that the crystal graph for each Schur module, each irreducible GLN representation, is going to be connected and have a unique highest weight element that we can identify it with. So in general, if we have some other representation and we define a crystal graph structure on it, we'll be able to look at the connected components of that crystal graph and use that to read off the irreducible representation multiplicities that we're after. Okay. Great. So let's return to our question now that we've gone over those tools. If we have an embedded variety in some affine space, and it carries an action by GL or a product of GLs or some other reductive group, how are we going to decompose its coordinate ring as a representation, or figure out the multiplicities of the irreducible representations within it? This is the main definition that I introduced with Abby and Alex in our papers. We say a Gröbner crystal structure for X is a crystal graph on the set of all monomials for the affine space that X is embedded into, such that when you restrict the crystal graph to just the set of standard monomials for our variety, it still forms a crystal graph. In other words, no edges of the crystal graph connect standard monomials and non-standard monomials. And if we have a Gröbner crystal structure, then by definition and by the whole theory of crystal graphs, we will immediately have a rule for the irreducible representation multiplicities in the coordinate ring, which will be something of the form, the irreducible representation multiplicity is the number of highest weight standard monomials of whatever weight you care about. So that's great. But in some sense, definitions are cheap, right? Like this definition doesn't mean anything unless we actually have interesting examples where we want to know the irreducible representation multiplicities, and we can actually construct explicit, useful Gröbner crystal structures. So in our papers, the main examples we think about are varieties like the classical determinantal varieties that live in the space of matrices. In the space of matrices, we can identify our monomial basis for our polynomial ring with m by n non-negative integer matrices These are just like the exponent vectors of the monomials, except we have a matrix of variables, so it ends up being like an exponent matrix. And then there's this lovely theorem from Danilov-Koshevoi and van Leeuwen about 20 years ago, which states that the Robinson-Schensted-Knuth correspondence gives a boldface GL crystal graph structure on the set of non-negative integer matrices. If you're not familiar with the RSK correspondence, I'm not going to give any details here, but this is a central bijection in algebraic combinatorics that has many generalizations and many interpretations, and this is the crystal interpretation of it. You can think of it as defining this crystal graph structure on non-negative integer matrices or on the monomials in this polynomial ring in a matrix of variables. Moreover, if we care about a group that's a Levy subgroup of boldface GL, so some product of GLs embedded inside here, then we also get those crystal structures for free just by deleting edges from this RSK crystal graph. Okay, so what are our main theorems? We call a variety in the space of matrices bicrystalline if the RSK crystal on our non-negative integer matrices forms a Gröbner crystal structure. And then by definition, by the general theory, if we have a bicrystalline variety, we have an explicit combinatorial rule for the irreducible representation multiplicities of its coordinate ring. Our main theorems are one, we give some large class of varieties that are defined by rank conditions. So there's some sort of generalized determinantal varieties that are bicrystalline. And then two, we give a finite algorithm which tells you it takes in a variety in the space of matrices, and then it does some computations and tells you whether or not that particular variety is bicrystalline. So some examples here, using the combination of the algorithms and the theorems, we're able to show that the classical determinantal varieties are bicrystalline. We can show that matrix Schubert varieties are bicrystalline and unions of them. So that includes alternating sign matrix varieties and some examples of nilpotent matrix Hessenberg varieties. We can show that double Bruhat cell closures are bicrystalline, which are sort of like a further generalization of matrix Schubert varieties. We can also do this for some things that aren't reduced. So we can look at the schemes corresponding to different sorts of powers of determinantal ideals, and those things we can also show are bicrystalline. And we can also look at at least examples of more complicated varieties in algebraic combinatorics, such as matrix matroid varieties, and show that some of those are bicrystalline as well. Yeah, so this is sort of a general flexible method. So there's a whole lot of different generalizations that we're interested in pursuing. Here are some that my co-authors are pursuing or that I'm interested in pursuing in the future. But I think I'll stop here to allow some time for questions. Thank you very much.
Thanks for a very nice talk. Let's thank our speaker.